This is one of a series of lectures produced by the Further Mathematics Support Programme for A-Level Maths Revision. In this lecture we're looking at the Edexcel Decision Mathematics 2 specification, and the topic is dynamic programming. The specification says that you should understand the principles of dynamic programming, including Bellman's principle of optimality. You should understand the term stage variables, state variables, and the use of tabulation to solve maximum, minimum, minimax or maxi min problems. Well, to explain some of those terms, a diagram below is a typical sort of setup for dynamic programming. The network shown starts at S and has arcs moving through the network to the final point T. The nodes are what are called the states, and at any particular stage where we're going from one state to another, the arc represents the action. Each arc has an associated weight, and it's the sum of these weights along whichever path we are using which gives the value of that path. Bellman's principle states that any part of an optimal path is itself optimal, and it's this that forms the basis of dynamic programming. What happens is we work backwards from the final destination T in a series of stages. These are normally numbered backwards, starting at 0 at T and coming back 1, 2 and 3 till we get to our start point S. So we start with stage 0 and we look at the possible actions that can be taken at that stage. So in this diagram, the possible actions in the first stage, stage 0, are ET, FT and GT. And at each stage there are different destinations depending on where the start state and the action that you take. So for example, in stage 1, if we start at C, then there's an action CE which ends up at state E, CF at state F, and so on. So working backwards, we can solve problems which, it says in the question, are maximum and minimum, so we can find the longest or the path of greatest weight, and the minimum, the path of smallest weight. But also the idea of minimax and maxi min problems are required. Now a minimax is such that the leg with the greatest weight is as short as possible. So as small as possible. So what we're trying to do here is to make sure that the maximum value that we meet on our path is as small as we can possibly make it. In a maxi min problem, the opposite is true. We're looking at the minimum values along the path, and we're trying to make that smallest value along our route as large as possible, so that we're trying to make the minimum weight along the route as large as it can be. So maximum, minimum, minimax and maxi min problems are required. Now we'll move on to look at a couple of exam questions which hopefully will explain those things a little bit in more detail. So the first question is one we set out in a table. It's quite long and involved, so it is worth spending a little bit of time just reading through to make sure you understand what the question is asking. So it says right at the start that Patrick is to take orders for his company's products, and he will visit 4 countries over the next 4 weeks. It says he'll visit 1 country each week, leaving from his office in London, and will only return after visiting the 4 countries. So he's starting in London, going through 4 weeks, and then returning to London. It says he will travel directly from one country to the next, and he wishes to determine a schedule of which 4 countries to visit. In the first table we've got the possibilities where he can visit, and then in the second table we've got the expected value of orders that he might achieve in each of the countries A to I. Finally, in table 3, we've got the costs of the travelling between various countries. The aim is to maximize the profit. So that's going to be the income at each country that he visits minus the cost of travel. And it says it's decided to use dynamic programming to find a schedule that maximizes the total expected income for these 4 weeks. We're given a table in the answer book to complete to do the dynamic programming on. And then the final part is to state Patrick's 2 optimum schedules. So we're expecting to find 2 particular ones which will give a maximum profit involved in this particular problem. So quite an involved problem. We've got to take the information in the tables and put it onto the dynamic programming table that you'll see on the next slide. Well, the first thing we need to do is to make sure that we understand how the table has been completed for us so far. So remember that we're starting at the end, as it were, so we're going to work backwards towards our starting point. And in the first stage, we can be either at H or I, and we're going to move towards London. So the states, 2 possible states are H and I. The actions are moving from H to London and I to London. So the destination in both cases is London. Now, how has the value been worked out? Well, that's the possible profit that's in the second table for H is indicated as 36 minus the travel costs, which comes from the second table. So that value 31 comes from 36 minus 5. Likewise, in the line below, that's moving from I to London. So this time the cost is 4, and the possible order values at I are 38. So we've got 38 minus 4 giving you the 34. Moving back then a stage to stage 1, this would be week 3, where the possible states that we can be in are F and G. The actions for state F have been completed for us, so I've indicated that on the tables. We can either do FH, so we've got to end up at H or I, so FH, so destination H, and FI, destination I. Now the values there, well, if we look at the table again, at F we expect orders of 29 multiplied by 100, so 2,900, and in terms of hundreds we expect the travel costs rather are 6, so we've got 29 minus 6. But then if we're going to H, if we look at the line above, sorry, the first line, H has got a current value of 31. So we have there 29 minus 6 plus 31 giving you 54. Similarly for FI, the destination is I, the same 29, but now the travel costs from F to I are 7, and the current value at I was 34. So we've got a total there of 56. The asterisk that's been put there is to indicate the largest of the values. Remember, we're trying to maximize, so in the first 2 lines we've got an asterisk on both those lines. But now for state F, our maximum value is 56, indicated by the asterisk. Well, now it's our turn then. So we're looking at G. G again has got 2 possible actions, so I'd always say put the actions in first of all. GI is the second possibility, and H and I are again the destinations. Looking at our tables, the orders that we expect are 27, so both of these numbers here are going to be 27. And the travel costs for G to H are 5, and for I to H are 6. If we end up at H, then we've got a current maximum 31, and if we end up at I, the current maximum is 34. Totaling those gives values 53 and 55. So the largest of those is the 55. We mark it with an asterisk. Well, that's the end of stage 1. So I tend to underline in my table now so I can got some clear idea of what I'm doing. And so we're now moving on to stage 2. In stage 2, then we can see from our table from the first table, there are 3 possible states that we can be in at the start of stage 2. Those are C, D or E. So putting those in on our table, then we need to say how many lines does each one take. Well, each one can move to the next country, and there are 2 countries, F or G, to move to, so we'll have 2 lines needed. So C, D and E can go in the table like that, with the possible actions being from C to F, C to G, D to F, D to G, E to F and E to G. The destinations are F, G, F, G, F and G. Well, for state C, I've indicated on the tables the appropriate parts. So C, the possible orders are 42. So both of these will be 42. The costs associated to travel to F is 6 and to G is 5. If we end up at F, going to the stage above rather, we've got there the maximum for F is 56. So there we'll have plus 56. And for the second one, if we move to G, we can see that its maximum is 55. The totals there come to 92 for both of them. I've jumped forward a little bit now to the point where stage 2 has been completed. At each part in the table though, I'm using the travel costs from table 3 associated with the start state and the destination at each point, and the order values from the countries that we are in at the current state. So for example, if we look at the line for the first line for D, then we have an order value of 41 minus 6, the travel cost, and that takes us to F. So looking in stage 1 for F, the current maximum value there is 56. So 41 minus 6 plus 56, giving us a value of 91. So for each of those different actions in stage 2, we've calculated the maximum values and indicated with an asterisk. Well, in stage 3, moving back towards the start, remember this is now week 1, there are only 2 possible states, A or B. But because we've got 3 destination states, C, D and E, each one is going to require 3 lines. So A will require 3 lines and B will require 3 lines. The possible actions, of course, are A, C, A, D and A, E, with destinations C, D or E. And similarly for B, we can go B, C, B, D, and B, E, with destinations again C, D, and E. The order value for A is 22. So each of these first three lines is going to start 22. And the order value for B is 17. So each of those three lines will start 17. The costs for A are 5, 4, and 2 respectively. So we're subtracting 5, 4, and 2. And for B, there are 4, 4, and 3. If our destination is C, the current value, maximum value there is 92. If it's D, it's 93. And if it's E, it's 91. Those are repeated below for C, 92. For D, 93. And for E, 91. That gives totals of 109. The next two are both 111. So those are both maxima for A. And then 105, 106, and 105. So the maximum value there is 106. That completes stage 3. So now we move on to stage 4, where there's only one state to be in at the start of stage 4, that's London. So we have to go from London to A or London to B, so with destinations A or B. Now a slight difference here, of course. In London we're not going to achieve any orders, that's our home, we're not actually looking for orders in London, so there's going to be no order value, or you could put 0 in there. But there is a cost associated for moving from London to each of the countries, and we can see those costs at the final at the top of the final table. So the cost moving from London to A is 5, and London to B is 3. Again, looking at A in the stage above, the maximum there is 111, so we can add on to that 111, giving us a final value of 106. Or if we move to B, we can see that the maximum there is 106. So subtract the 3 gives us 103. Therefore, our maximum, our optimal route is going to give us a final value of 106. And remember, that's 106 hundredths, so it's 10,600. Well, to find the schedule for this, we start at the end of the table with the asterisk that we've got there, 106, and look at the path that it says that we should follow, so the destination. So from London, it says we should go to A, and then we simply move to A to see where the next asterisk is. Well, when we look at A, we see there are two possibilities. The destinations are either D or E. So perhaps we should do that as a separate route, so we'll have London, A, E as a completely separate thing. Well, let's follow the route for D through our table. If we go to the next one up, we'll see that in D, the asterisk is pointing us to G. And then moving on up again, in the next stage up, we'll see that the G is moving us to I. And then of course we come back to London, the final stage. Going back down to see what's happening in the meanwhile to the route that went to E. If we go to the asterisk in E, we can see that the next point of that is F. So the other route is going E, F. Moving up to F, to see where the asterisk is there. And that again is at I. And on from I we get back to London. So the two routes that are possible to give us our optimum income of 10,600 are London A, D, G, I and back to London, or London A, E, F, I and back to London. We'll look at the marks allocation for that. Basically at each stage there was an M1, A1 available. So in the first stage, also M1, A1 in the second stage, although there was a second A1 if you completed that stage correctly. Again, M1, A1 and A1 in stage 3. These were follow-through aids as well at this point, so that if you'd made an error then you could still pick up marks. And a final M1, A1 in stage 4. So of the 11 marks, 10 available there. There was an extra, well, 11th A mark for getting the correct value. Again, follow through. So if you hadn't quite got the right value, if you'd read the correct maximum off your table, then you would get that A mark there. The other two marks were B marks for reading off the schedules from your table. I will look now at a different type of question. This is from the June 2010 paper. And here it says that figure 1 represents the maintenance choices a council can make and their costs in £1,000s over the next 4 years. So the council wishes to minimise the greatest annual cost. So we need to use dynamic programming to find that. In other words, find a mini-max route from S to T. It says we should state our route and the greatest annual cost incurred by the council. As a supplementary question then, we're to calculate the average cost to the council. Well, I've started this off by showing the different stages on the network. I've called them stage 1, 2, 3 and 4. The actual number doesn't matter. Sometimes it starts at 0 and sometimes at 1. But we are working from the destination, final destination T, back towards the starting point S. On the table I've also indicated the possible states at each stage you can be in and the actions and the final destination. So I've transferred the arcs and the nodes from the network onto the table. That you can do before doing any of the calculations. The next stage now is then to start putting in values. Well, the values are the maximum values first of all, and then we want to minimize those maxima. Well, for the first stage, of course, there are only one value in each of the particular states. So G has 17, H 21 and I 29. So these are all going to be the smallest maxima at that stage. Now this is where a minimax problem and a maxi min problem differ from the straight maximum and minimum. The next values we need to look at are finding the maximum of the current action, which is DG, and if we look at the diagram, DG is 22, and the value if we're at state G in the line at the top line of the table. So that one is 17. Now the maximum of those is 22. If we look at the action DH from D, then the action is equal to 31 and H has a value of 21, so we want the maximum of 31 and 21. And of course the maximum of those is 31. Now we've got to indicate the smallest maximum for that state D, so that therefore is the 22, and that appears with an asterisk. I'll just finish off this stage in a similar way. So for state E and action EH, we've got the maximum of 34 and 21, which is 34, and for action EI, it's the maximum of 39, and I has a current value of 29, so that's 39. And we want the smallest of those, the minimum value of those two for state E, and so that's the 34. And finally for F, well, there's only one action from F, and that has a weight of 52, so we're looking at the maximum of 52 and I 29, and of course that is a value of 52, but for that particular state that's our current minimum. I'll just jump forward again, this time completed stage 3, doing exactly the same, looking at the action and then the maximum of the weight for that action and the current value of the destination, the current minimax value of the destination, and at each stage marking which of those gives me the minimax. Finish off then with the fourth stage. SA has a weight of 37 and the current minimax for A is 38. The SB has a weight of 39 and B has a minimax of 44, so that gives me 44 as the minimax value. And finally SC has a weight of 41 and C a current minimax of 36, so that gives us 41, giving me then the final minimax value of 38. We can find the root by tracing through our table, looking at the asterisks. It goes from S to A, and in stage 3 A goes to E, in stage 2 E goes to H, and then finally to T. And the greatest annual cost is our value of 38, but of course that is £38,000. To get the average annual cost, then we need to take each of the values at each stage. So going back, we'd have the following. SA is 37, AE is 38, EH 34, and HT 21. Divide that by 4 to give the average, but remember this is thousands of pounds, and that comes out to be £32,500. Like the previous question, this is marked very, very similarly with an M1, A1 at each stage. So the first stage, and then M1, A1, A1 for each of the second two stages. with a final A1 at the end. That gave there a total of 9 marks for the table. There was then an M1 A1 for quoting the correct route and getting the correct route rather, and the greatest annual cost, and M1 A1 for calculating the average cost. Maxi Min values are done in a similar way. This time you're writing down the minimum that of the values, the weights at each stage, and looking for the maximum of those minimums. So it's the opposite of what we've just done in this one. So be careful with the difference between a mini max, which we've just done. We've looked at the smallest of the maxima on the route. That's the mini max. And a maxi min, where we look at the largest of the minimum values on the route. Okay, well, that's the end of this particular lecture. You'll find other lectures on the website, which is www.furthermathematics.org.uk.